Hi, I'm Sungrae Kim from Seoul Tech. Today I'm gonna review the paper that I wrote. Uh, the title is Zero-Centered Fixed Point Quantization with Iterative Retraining for Deep Convolutional Neural Network based Object Detectors. And it was published in the Access 2021. The order of presentation is as follows. Next is the introduction, then the method, then the experiments, and finally the conclusion. The first, introduction. As you know, with the development of deep neural networks, the accuracy of object detection and classification increases dramatically. However, because the DNN uses many layers, a large number of parameters are required, which significantly increases computational complexity. To solve this problem, two representative methods have emerged. The first is pruning and the second is quantization. Pruning is the method that reduces the number of parameters by removing unnecessary weights, filters, and layers, resulting in less complex networks. However, data quantization only reduces the bits that are allocated to the weights and activation parameters. It maintains the original network structure, so it is easy to apply regardless of network type. Going back to 2021, most recent quantization studies have focused on int quantization with integer parameters and floating point scale factors to prevent an accuracy decrease in networks that perform image classification. Zhang found that a reduction in accuracy does not occur when using only 4 bits for both weights and activation parameters, even for the ImageNet dataset. However, in an embedded platform or hardware accelerators environment, it is much more efficient to change the weight or activation parameters only to a fixed point format. Floating point arithmetic costs approximately about 4 times more energy for addition and 16 times more energy for multiplication than fixed point arithmetic in hardware architectures. Accordingly, fixed point format-based quantization studies have been conducted. Andrich changed the distribution of weights multimodally, but didn't concern about distribution of weights that is not distributed symmetrically. Lin uses the signal to quantization noise ratio to minimize quantization error, but mathematically minimizing errors does not necessarily lead to an accuracy reduction. Now I'll introduce the proposed method. At first, I'll let you know the overview of proposed quantization method. Then, I'll introduce three main ideas called zero-centered convolution, iterative retraining, and finally, adaptive bit allocation. Here's the overview of my paper. I conducted the quantization with deterministic quantization, not stochastic quantization. As I said before, I quantized the weights and activation parameters with fixed point format for energy efficient hardware environments. And I didn't claim any parameters using maximum and minimum value as a quantization range boundary. Iterative retraining method is used to minimize the accuracy drop caused by quantization. Use hardware-friend quantization method to quantize non-zero centered distribution. I conducted image classification with VGG7 network with Cipher10 dataset. For object detection, I used YOLO V3 and V4 network with COCO dataset. I conduct the quantization dividing them into two parts. First is zero-centered weights, and second, the mean of weights. Zero-centered weights are quantized and retrained iteratively, gradually increasing the quantization rate until the Q rate becomes 1. Those two parts are added to get a better approximate result for the original calculation. The first main idea, zero-centered convolution. As shown as below, the median of each layer of various deep neural network is not a zero. Weight distribution of deep learning network is not distributed around zero. But as you know, fixed point quantization should have zero and symmetric quantization points. To address this issue, this paper uses a zero-centered effect that moves the center of weight distribution to zero, subtracting the mean from each weight. However, the zero-centered technique of weight parameters accompanies change in the convolutional arithmetic process. In order to maintain the results, the mean is multiplied separately with the input data, expressed as x in the formula below. Since the multiplication requires fewer operations, the proposed method has almost no difference in the amount of operations compared to the original convolution operation. Ambiguous values between adjacent quantized points present a challenge in determining which quantization point to quantize. Ambiguous values refer to values that may belong to quantization point on both sides, such as the red circles in figure B. No matter which point those red circled weights go to, they may occur small quantization error. As you can see below, the table shows the proportion of ambiguous values before and after retraining. In the three different networks, the proportion of ambiguous weight exceeds 20% in non-trained network. I only quantize some values close to the quantization point and retraining. Only less than 10% of the values in VGG7 network had an ambiguous value. Using these characteristics, quantization is performed starting from the values close to the quantization point, then fix them, and then retrained. Conducting retraining, the range of quantization gradually expands, like going from figure A to C. The final method is adaptive bit allocation. DNN models have a significant depth of layers, so the minimum number of bits required to express the weight parameter is different for each layer. In specific layers, even if the number of bits used to express the weight parameters is reduced, the MAP rose. I measure network accuracy by changing the bits of each layer, and the bits that showed high accuracy was considered the most optimized bit of each layer. So I adaptively determined the number of bits of each layer in its network using grid search method. Figure A and B show the most optimized bit of each layer of ULV3 and ULV4 networks. And next, experiments. I conduct quantization in image classification and object detection. In image classification, I use Cyper10 dataset and VGG7 networks. Our proposed method increases quantized models accuracy. Especially with two of mentioned methods are being adapted. The accuracy drop is only zero point 0.1, even the weight and activation is tied to 4 bits. Comparison with other fixed point quantization methods, our paper gets higher accuracy. In object detection, I use YOLO V3 network with COCO dataset. Performance degradation is extremely severe even if it is quantized to 8 bits with basic deterministic quantization. The average number of bits required for weight parameters can be decreased to an average of 6.58 bits while maintaining the same MAP with proposed 8-bit quantization. I also quantize YOLO V4 networks. Performance degradation is more severe than YOLO V3 when basic quantization method is adaptive. The average number of bits required for weight parameters can be decreased to an average of 5.99 bits, while achieving higher MAP than proposed 8-bit quantization. The visual evaluation is as follows. There's no visual difference between the proposed method and the pre-precision networks. Lastly, the conclusion. Fixed point-based quantization methods specialize for hardware to compensate for the problems of floating point-based quantization methods. So I only used fixed point numbers. An adaptive application method that can expand to the object detection is proposed. This paper gets higher accuracy in Cypher10 dataset than the existing fixed-point quantization schemes. Also, when applying the proposed techniques to YOLO V3 and YOLO V4 networks, the MAP is similar to that of the original networks using only approximately 20% of number of bits for weight parameters. Thank you for listening.